So this is the tougher of the three examples. It's a little tricky because it's got that a value, the 2x squared. And so to determine the perfect square that's going to result in this, it's sort of buried one more layer. So easiest thing to do is to factor that 2 out if you can. So here we've got ourselves a little bit closer to seeing that perfect square. We've got the brackets here, but of course that x squared minus 4x needs a third term in order to really encompass what that square, that perfect square is going to be. And so now it's time for us to start engineering that, okay? Okay, so how do we figure out what we need? Well, you got to look at this term here and realize that, okay, so how do we get this negative 4x term? Well, it would have come from two x terms that are put together. So basically, you need to find what half of that is. And half of what that is going to be that second term in your perfect square. So it's going to look something like this. So because of that negative 4x there that we see, we know we have to start with this perfect square here. Because if we do this perfect square, we'll get that negative 4x. So we need x minus 2 inside that squared bracket. So there's our perfect square that we would aim to create. But again, we have to force it. So let's expand this perfect square to see what we're really dealing with. So we would have to FOIL this and then include the 2, distribute the 2. Okay, so there's what we get when we FOIL this thing. And the tricky part here is this little addition at the end here is the thing that's missing in our original equation that we're going to have to put in there to create our perfect square. Keep watching. And there we've collected like terms. Okay, so now we can see that what we're really needing to do here to engineer this perfect square is adding 8. We can't create the perfect square unless there's an 8 there. Now if you look at the original equation, up here you'll see that 2x squared, just like here, minus 8x, right here, and then plus 10. We knew that wasn't really going to work. What we really need is plus 8. So we're just going to put plus 8 into the original equation. We're going to add it to the right side, and that's going to allow us to create that perfect square. Really, we're going to be able to create this, okay? Now, the plus 10 at the end, we're going to have to just kind of work that in and whittle that down like we did last time. So if we go back to our work with the equation here, what we'll need to do is add 8 so that we can generate that perfect square from this structure here. But we have to also subtract 8 to make sure that that equal sign is maintained. It wouldn't be fair, it wouldn't work if we didn't do that. So now we're going to take that 8 and it's going to become part of this structure here and going to form that perfect square that we were looking to create. So there, now we've got that structure put together with the plus 8 that we needed. We've now formed this perfect square, 2x minus 2 squared. Now we'll have to add in the other bits. We've still got our plus 10 there. And we have to add our last term here, negative 8, to make sure that the equal sign is still true. Okay, so we just put that plus 10 and negative 8 together. At the end, we get plus 2. So that's it. We're done now because you can see here we have our vertex form of a quadratic function. We've got our a value here is 2, our h value, negative 2, and our k value, positive 2. So we've just transformed this from the original standard form by figuring out what perfect square we needed. We decided what that would look like. We discovered that we needed an extra 8 to be included in the equation for that perfect square to happen. We added that 8. We kept it fair by subtracting 8 as well. We formed our perfect square, and then we just whittled down those last two numbers. So now we have our vertex form. That was the tricky one with that coefficient of 2. There are certainly more of those, but I think we've pretty much covered what we need to. So good job, good effort. Way to stick to your guns. Now that you have the power to change your expressions from standard form to vertex form and vice versa, you really have everything that you need to look at other problems, scenarios that ask for you to unlock certain important critical points. For example, what is the vertex of this function? Well, the vertex of a function is hard to see in standard form, but much easier to see in vertex form. So you may decide that the vertex form of the equation is the one that you want to use. Oppositely, the vertex form, it's much harder to see the zeros in the vertex form. You really need the standard form to get access to the zeros quickly and efficiently. So having a really good working knowledge of both expressions is really, really key. And so now in the next lesson, I'll have you guys working with a standard form equation and or a vertex form equation and pulling out those critical points. What's the vertex? What's the y-intercept? When does the function become 0? Of course, the zeros, those are your roots. Hopefully that now that you sort of have this versatility, you'll be much better off, more powerful, and hopefully be able to tackle those practical, situational problems much better. Okay, good luck.